Hi, welcome back to the part 3 of the natural language processing lecture of the course Big Ideas in Artificial Intelligence. So in part 2, we talked quite extensively about how to extract or learn the meaning of a word. That is, how do we extract a vector representation of an individual word that is going to tell us which pairs of words are similar with each other and which pairs are dissimilar with each other. And how we got there was to think about how the context gives rise to the meaning of individual word. That is, we need to know where an individual word appears in order to tell the meaning of this word. And then how did we get the information about the context? We went through a large amount of text in order to collect the statistics about the context in which each individual word appeared. However, as it is understandably so, words are only the very first step in this ladder of natural language processing that includes natural language understanding as well as the natural language generation. So we want to, in fact, go further than just thinking about the meaning of an individual word. So if the meaning of an individual word arises from the context in which it appears, perhaps we can also say that the meaning of the context, that is the meaning of the text itself, arises from the composition of individual words that make up this text. That is, it is in fact a single coin, and we looked at one side in order to extract the meaning of the word by looking at the statistics of the context in which this word appears, together with the idea of matrix factorization or compression. The other side turned out to be that by looking at a sequence of individual words, that is the text, and how these individual words are composed, we can now tell the meaning of the text itself. So it's the two sides of the same coin, and then we're going to look at the other side in part 3. So what do we get by composing or considering the composition of individual words? It turned out that one of the most important thing that we gain by composition is so-called disambiguation. So what do I mean by disambiguation? Think of any word. In this particular case, let's think about a word notebook. When you think about notebook, depending on which context you are in, that is what you are thinking earlier or what kind of sentence you heard the word notebook in, you may actually you may think of one of at least two different senses. The first sense would correspond to notebook as in something that you write on, such as diary, sketchbook. On the other hand, the second sense is the notebook as an electronics device. And the interesting thing is, because notebook can appear in these two different possible contexts, the word vector that corresponds to notebook extracted or the learned based on the procedure that we talked about in the second part will in fact encode multiple dimension similarity. The example that I'm showing you on the screen is not a made-up example. In fact, this is the projection or the dimensionality reduction of the high dimensional word vector of notebook and its nearest neighbors. And then what we see is that the first dimension corresponds to the first sense of the word notebook, while the second dimension corresponds to the second sense of the word notebook. And it really automatically arises. However, what this in fact means is that by just looking at the word vector of this word notebook, we cannot really tell precisely what this notebook means because there could be multiple possible meanings of this notebook. So what we need is to now consider the context, that is the words that surround this particular word notebook, in order to resolve this ambiguity. So you see You see where disambiguation comes from. Let's take as an example a sentence I just made up. That is, I use a notebook to join the lecture online. Now in this word, in this sentence, notebook could very well mean either book or electronics. But because I know that at the end of this sentence, there is a word online, I can disambiguate or resolve this ambiguity and then very confidently say that this notebook, in this context, this sentence, refers to an electronics device. So that is the second dimension of the meaning in this word vector space. Now, of course, then the question is, how do we compose these word vectors? Do we simply sum them? That sounds a bit dumb, because if we simply sum all these word vectors, then it won't know about the order of the words, nor can cancel each other. So we need something more smart. And it turned out that in 2015, in fact, I, together with my collaborators, Dima Badnau and Yoshua Benjo in Montreal, we came up with this idea called attention mechanism, although we didn't call it attention back then. What this attention mechanism does is, given a sequence of word vectors of the sentence, so in this case, we're going to have as many word vectors as there are words in this sentence. I use a notebook to join the lecture online, period. And then this attention mechanism is going to take the word vector of the word that we want to resolve the ambiguity of, and then compare it against each and every word in this sentence. And every time it compares the word vector of the notebook against the word vector of another word in this sentence, it's going to assign so-called attention weight or the attention score. And it's going to do that for every single word in the context. And eventually, we end up with the sequence of the word vectors. And then for each vector, we have the associated attention weight with respect to the word that we are interested in. That is the word notebook in this particular case. Now, if the word in this context is important for resolving this ambiguity, then that word is going to receive a very high attention weight, while the words in the context that do not contribute to resolving this ambiguity or this ambiguity will not receive high attention weight. And using these attention weights, we are going to compute the weighted sum of all these word vectors in the sentence in order to compute this so-called contextualized word vector of notebook. So this is a vector that is very specific to notebook because we computed this attention weights, that is a relevance of each and every context word with respect to the center word notebook. And then it is word vector still because we get one vector of this word. But now this one knows that the notebook in this sentence refers to an electronics device, not something that you write on directly with your pen. And this was termed, or this wasn't termed initially as the attention mechanism, but it has become known widely as attention mechanism. Now then, using this attention mechanism for each and every word in the input, we now can get for any sentence a sequence of contextualized word vectors. And we can consider this sequence or a set of contextualized word vectors, so this entire set, as the contextualized representation of the entire text, or that is a sentence. So we use this attention mechanism to compute the contextual word vector of each and every word in this input sentence. And then the set or the sequence of these resulting contextualized word vectors is how we represent the meaning of this sentence. And it turned out that this kind of disambiguation of word senses often can benefit from having multiple layers of such resolution. The reason being, in this particular example, we were able to easily disambiguate the word sense of notebook by looking at not just one other context, words in the context that was online. However, when we think about resolving the ambiguities that are very, very complicated, we may need to look at multiple words in the context sequentially. So we may need to look at online first, and then given that we know now that there is online in this context, maybe we want to look at lecture next. So there is the chain of context words in the context that need to be considered one at a time in order for you in order for this neural network now to figure out what precisely each and every word in this sentence means. Thereby, we can know the meaning of the entire sentence. And then when we have this stack of attention mechanism followed by nonlinear projection, we call this neural network a transformer. Now the question is, how do we then train this neural network? Because although I use attention mechanism and then use it as if it's given, this black box called attention mechanism is not designed nor given naturally. We somehow need to figure out how to make it so that it resolves all those ambiguities automatically. You've taken multiple lectures in this course already, and then this is already the third part of this lecture on NLP, so you can probably guess. Yes, we are going to use a large number of examples. But then, having data doesn't really mean anything if we don't know what we should or what we think these neural networks should do with this data. And then to figure out what we need this neural net to do or be able to solve in order to learn to extract the meaning of the text, we need to think about what we can do. We, as in ourselves, we can do had we known the meaning of a sentence. And one thing we can say for sure, if we think we know the true meaning of a given sentence, is that we must be able to fill in missing words with very plausible words. Because we know language and then because we know the meaning of the sentence, when we are given a sentence, I used a blank to join the lecture blank period, we can now tell what are the plausible alternatives that can be used to fill in these missing bits. The first blank probably can be filled up by a word like notebook, laptop, phone, or more recently, Zoom. Perhaps the second missing bit, that is after lecture, we can plug in online or remotely. This fact that we can fill in these missing words implies implicitly that we do have a very good sense of what this sentence or any given sentence means. Another example of such an activity is to completing a partial sentence, which is shown to you on the right side of this slide. Given I use a notebook too, so all of us who understand language and know the meaning of any given text can figure out what are the plausible completions or the endings that we can plug in to make a meaningful sentence. I use a notebook to play StarCraft every day. At least that's what I used to do when I was a freshman and sophomore back in my undergrad years. I use a notebook to train a convolutional network. Perhaps this is what Professor Yan LeCun did when he was working on convolutional network, or more like inventing a convolutional network back then. Or these days, or if we think that the notebook can be used with the meaning, if we consider, I'm sorry about that, let's rephrase. If I use the first sense or the meaning of a word notebook, that is the something that we write on, I may be able to complete this sentence by saying, I use a notebook to record my ideas. So the fact that we can fill in these missing bits tells us that we know the meaning of a sentence. And then perhaps what we want to do is to train this large transformer that is extracting this set of contextualized vectors via multiple layers of attention mechanism to be able to fill in missing words. And then this is the idea behind so-called masked language modeling. And any transformer that is trained as a masked language model nowadays is often referred to as BERT. How do we train this BERT? We start with this transformer, and then we're going to give as the input a sentence from a large data set we have after masking out or leaving out some of the words randomly. And then this BERT is going to extract a contextualized word vectors. And then from there, we ask BERT to be able to reconstruct these missing bits. So in this example on the slide, the original text is I used a notebook to join the lecture online. Now, BERT, however, before we give this sentence to the BERT, we're going to randomly leave out notebook and online from this sentence and give I use a mask to join the lecture mask period to BERT. And this BERT is going to extract the contextualized word vectors. And then from the fourth and the second to the last word vectors, it will try to predict these missing words. And then if there is a discrepancy between the prediction and the correct one, that is going to work as a signal that we use in order to train or tune all these attention mechanisms that learns to compose the word vectors into contextualized word vectors. And for that, we use the idea of the backpropagation, which is a very standard way to train a neural network. Now, once we train this BERT, this kind of model on a very large amount of data, does it actually learn so-called contextualized word vectors? It turned out that that's true. This is a figure I have adapted from the Conan, Rafe, Yuan et al. 2019. And then this is a really nice demonstration of this power of attention-based composition of the word vectors in order to extract contextualized word vectors, where each contextualized word vector really tells us precisely about the sense, the meaning of the particular word within this context. So what they did was to look at many sentences from Wikipedia that contain a word lie. And then for each sentence, you feed the sentence into a trained BERT and then let the layers of attention compose these word vectors until the very end, where we get a contextualized word vector corresponds to the word lie in the input. And these vectors, we collect all those vectors and we use a technique called UMAT in order to project these high dimensional vectors onto non-linearly onto a low dimensional, in this particular case, 2-dimensional space. And what we do see is that these contextualized word vectors very naturally form clusters based on the meaning or the sense of this word lie. On the top left corner of the presentation slide, you see that there is a cluster of all those sentences in which lie was used to refer to the lie in mathematical sense. On the other hand, when we look at the top center portion of this plot, we see that a lot of sentences are used lie, this word, in the sense of falsity or making a false statement. And then we do see all these clusters according to how this word lie is used. And then this is a perfect demonstration of how attention mechanism together with the word vectors allow us to extract these contextual word vectors and then thereby allow us to extract the meaning of the sentence or any kind of text beyond just an individual word. And then this BERT or mask language modeling that uses the attention mechanism in order to compose word vectors in order to get the representation or the very good meaning representation of a sentence has become a standard approach in recent years in natural language processing. And in this particular case, the standard approach consists of 3 steps. First, we train a BERT on a very large data, such as Wikipedia or all the text on the internet. And for this, we actually don't need any labels. All we need is just text. We are creating all these labels automatically in the time of training. How do we do that? By simply leaving out some of the words in each sentence and then asking BERT to reconstruct those left out words. So that was the idea of the mask language modeling. Once this BERT is trained, or we can call it now pre-trained because we're going to train it further, we attach a classifier on top. Just like the multi-layer perceptrons or the fully connected networks from the computer vision lectures that you have already taken. And then we fine-tune the entire network that consists of this BERT that extracts the contextualized word vectors and this newly attached classifier on top of that. Because as soon as we attach it, it just has become a one large neural network. So we can use the standard backpropagation algorithm and the stochastic gradient descent to train the whole thing on a very small amount of label data. It turned out that because these contextualized word vectors are capturing all these important meanings, you don't really need too many manually labeled examples in order to build a very sophisticated natural language classifier. So in this third part, we have talked about how we can go beyond the meaning or capturing the meaning of an individual word by learning or using attention mechanism that is learned to compose these word vectors to form a set of contextualized word vectors and how this set represents the meaning of the text in which all those individual words appear. In the next part, after the break, we are going to talk about the other side of natural language processing, that is natural language generation.